Hey everybody, welcome back to our Materials Informatics playlist. I'm Taylor Sparks, the University of Utah Materials Science and Engineering Department. Today we're talking about large language models in material science, right? And this is a really big deal. Large language models are the most exciting things that have happened to AI in my lifetime, right? They have really transformed it in a pretty dramatic way. And that has also translated to the field of material science, things they're making possible. So let's step back and talk about AI and language, big picture. If you look at the timeline of AI advances, it has always been applied to language from the beginning, way back in the 50s, right? When they were doing things that were sort of rules-based approaches for artificial intelligence. And then as that transitioned to the 80s and early 2000s, now you saw statistical approaches and the first sort of network approaches. And then we saw for the first 20 years of the 2000s, the rise of deep learning and neural networks. And that really changed in about 2019 because from then forward, it has been dominated by large language models. And in all of these areas, it was applied to language, right? So we need to define a few terms that get thrown around kind of as if they were the same, but there are some differences. So first off, natural language processing, or NLP. This is simply a branch of artificial intelligence that gives machines the ability to read, understand, and derive meaning from human languages. Language models are algorithms that predict the likelihood of a sequence of words, and then large language models are just language models like defined previously, but now deployed at a comprehensive scale. Okay. Before we dive into large language models, let's set the stage by talking about a little bit of the math that took place in pre-neural network natural language processing. Okay, so for example, one of the early things that it would do was called bag of words. And in bag of words, you represent the words as if they were a multi-set of words, disregarding grammar and even word order, but you hang on to multiplicity. So I think of this sort of like one hot encoding, right? When we go back to think of our composition-based feature vector, if you have a vector where every element in the vector represents whether or not an element of the periodic table is present or not, that's kind of how this worked. You put a 0 if that word never shows up in the document, but you put a 1 or a 2 or a 5 if that word shows up, 1, 2, or 5 times. It's the same thing, right? The value that gets stored there is the word frequency, and then the spot in the vector represents all those words. So that gives you a way to represent the information in words, right? Well, once you do that, you can do all sorts of things. You can do like term frequency, inverse document frequency. So this is now a numerical statistic that reflects how important a word is to a document or some collection or corpus. So you're going to take the number of times a word T appears in a document and then divide it by the total number of terms in a document, right? That would be one measure. And if you multiply that by the log of the total number of documents, divided by the number of documents having that term, that is term frequency, inverse document frequency, which is going to be a measure of how important different words are. Okay. Here's another one, n-gram models. N-gram models are awesome because they build off what we just learned about in our previous videos, our probabilistic machine learning models, right, which were all based off of conditional probabilities. This is the same thing. It uses conditional probability to predict what the next item in a sequence will be based off of a function of the preceding n-1 preceding items, right? So if you have like your word and you're trying to predict what that next word will be, and you knew what the previous words were, like the previous 5, 10, 20 words were, then now it's a probability. It's a conditional probability. It says, what's the probability the next word is cat, given that the previous words were the quick brown fox jumped over the lazy, cat would have a different probability than dog if you had seen lots of examples of words, right? So this is really a way of thinking about it as in terms of max likelihood estimation for the next word based off of some corpus of text. There's latent semantic analysis, a little more complicated. This is analyzing relationships between a set of documents and the terms that they contain by producing a set of concepts related to the documents and terms. So they create this term document matrix. They decompose that into U, sigma, and BT, where sigma is essentially showing the ranked order of these values. It's a way to learn relationships between words. But really, the big breakthrough came with word embeddings that showed up in the neural network era. And there's two big ones. There's GLOVE, that's global vectors for word representation, and there's word to vec. And these have since, there's better ones since, but these were important at the time. And they allowed us to think about embedding information in a vector that allowed it to be, the vector could shift, right? So this graph is a common one you'll see, where imagine in document X, you have the sentence, gave a research talk in Boston, but in some other document you had a science lecture in Seattle. Those aren't the same, but they're similar. In fact, there's key words which get shifted, like the word embedding for Seattle and Boston. Maybe there's like a shift that you could shift from one to the other. Gave and had, research and science, talk and lecture, right? There's a shifting. If you embed things correctly, then sentences that are very similar to one another, like these two, should be able to be shifted, right, a little bit in terms of their vector and still preserve the overall sense or meaning, right? At least it's a pretty good indicator that you now have a vector that represents meaning based on words, okay? So how do they work? Well, word to vec, there's two versions of it. There's continuous bag of words, CBOW, right? And then there's skipgram. Let's do skipgram first. Skipgram takes a target word, so let's call it WI, some target word. And then the model is going to predict what the surrounding words would be, right? These are going to be your context words. We'll call them WO. So we do that with a softmax and a conditional probability, where you see you've got this exponential of, right, VWO, transpose VWI, and then we're taking that divided by the sum over all the different words. So essentially, the V vectors are representations for the words. Big W is your vocab size, and we're really just trying to maximize the probability for all correct word concept pairs in a corpus. So it's another conditional probability. And then continuous bag of words is similar to skipgram, but it inverts the role of the target and the context words. So now this one says, given some context words, conditionally predict what the target word would have been. So it's actually just the opposite. Glove does something slightly differently. It does a matrix factorization and a local context window, right? So it constructs some explicit word context. So this is a word co-occurrence, for example, matrix, by counting how frequently a word appears in a context. So when you see fox, how often is the word lazy nearby it, right? The quick brown fox jumped over the lazy dog, right? Because that's a very common sentence in literature, like there would be a high word co-occurrence there, right? That matrix would tell you that's a common or frequent word to find in the context of the other or group of other words, right? So this co-occurrence matrix Xij is done for each word in some context of the word J, meaning they're just found with one another. Therefore, once you've done that and represent it that way, now you can build an objective function that trains embeddings by directly relating word vectors to the probabilities that those two words will be found together. And then you minimize the difference between the dot product of the embeddings and the log of their co-occurrence probability. Okay, that's at least some of the math that happened to describe how we were even representing words as numbers in the first place. Okay, so what next? Well, natural language processing uses the same sequential algorithms. Now that we've got a good representation, the algorithms that get used, they're really just the same ones that we've learned about. We've learned about sequential data in the past in this series, things like recurrent neural networks, long short-term memory, gated recurrent units, and of course transformers. And language models they use these exact same algorithms that we've seen before, but now they're using them with words. In fact, in some cases, they were invented primarily for words, not for other stuff. We've instead taken something that was invented for language, and we've adapted it to all sorts of other things. That's actually predominantly the case. Okay, so large language models, they're simply very big versions of these algorithms, and they're mostly transformers. So why are these so big? I like this. This is from a 2020 paper from Kaplan called Scaling Laws of Neural Language Models. And in his paper, he argues that intelligence, right? We've all used things like ChatGPT, and sometimes it gives really dumb answers. And then you've seen instances where it seems to do a really good job and give very intelligent answers. In this paper, they argue that the overall intelligence is actually sort of a continuous, it's a sum of the model size, the data size, and the compute size, right? And what's really exciting is they point out that there's essentially like exponential growth in all of these areas. We have models with more and more parameters. Like think of like the very first transformer, BERT, right? That thing showed up with 340 million tunable parameters. Now compare that with GPT-3, which has 1 trillion. And my gosh, now in 2024, it's probably continued to the tens or hundreds of trillions. Who knows? Like they're much, much larger still. Same thing is happening with data, right? Global data generated annually. This isn't material science data, just data is also on an exponential curve. And compute is also changing. The rise of GPUs and our ability to compute in parallel via these GPUs and other approaches is also really taking off. So it's no surprise that the early sort of language models that you saw really pale in comparison to what we're seeing now. I remember my very first time I saw a language model, it was Talk to Transformers, which was based off of GPT-2, right? Early stuff. That was back right mid 2019, as it's shown here. That was an 8.3 billion parameter model, right? And I remember at the time you could ask it to tell you a joke like a Jedi, a Sith walk into a bar, finish the joke, and it would do not a great job. And now you can ask these, language models, the modern state-of-the-art ones today, to tell jokes, and they're actually pretty good. And that's, I think, to me, has been considered sort of a Turing test. If something could be funny, if it can be humorous, something that is really hard for AI to do, that's pretty impressive. So, anyways, this is I think exciting because this is showing how fast models are getting better. Okay. That said, there have been some haters that really don't think this is intelligence. There's this tweet, which I don't think has aged particularly well, by Yann LeCun, a polarizing figure. He's leading, last I heard, he's leading AI at Meta, where he says, on the highway towards human level AI, large language models is an off ramp. I don't know. I mean, I get what he's saying. They don't generalize in the same way that humans can, and yet they seem to be on a path towards really impressive outcomes, and they're allowing us to do really human-like things already. So are they as good as humans? No, but also kind of yes on some tasks, right? They don't generalize as well, but boy, they can do some things pretty great. So let's look at a few milestones in large language model development. Here's just 4. There's many others, but here's 4 big ones. The first one is going to be our generative pre-trained transformer, or GPT. So if you've used ChatGPT, this is the GPT part of that, right? This was invented, of course, by OpenAI. These were a new series of models that really set benchmarks in this area. They were trained on lots and lots of data, and they were able to generate coherent, contextually relevant text based off of some sort of given prompt, like tell me a joke, or write a research paper on, or so forth. GPT-3 has become the most widely known, and that's because ChatGPT used GPT-3 or 3.5 in the early days. And the things that they can do are things like text generation, tell me a story, or translation. Here's this phrase in English, turn it into Spanish, or summarization, right? Read this wiki article on the causes, on whatever, on Franz Ferdinand, and tell me why he was important. Question and answering, so much more. Another really important one was BERT. This happened before that. This was back in 2019, right? This was the bidirectional encoder representation from transformers from Google. This was a really significant shift in how information gets processed because they introduced transformers here for the first time. Really big deal because the transformer, because it's looking at all word pairs as opposed to just some sliding window, this allowed us to really grasp concept and context for different words. So they understand what does the word mean in the context of the overall, block of text that it's investigating, which was really, really effective in understanding, nuances of language. So this did some of the same tasks that we saw GPT do. How about T5? This is text-to-text transfer transformer. This is also by Google. This came later. And what's slick about this is that it transformed all NLP problems into a unified text-to-text format. So the input and the output are always text strings, and this simplifies training process. It allows the model to be applied across all sorts of different tasks. Once you convert something to text, now you can use that same model. We're actually using this in one of my research approaches right now as a conditioning tool. And then there's XLNet. This came out of Google Brain and Carnegie Mellon. And this introduced, what was slick here was the training strategy that allowed it to outperform BERT on several different benchmarks. It used a permutation-based training method that allowed it to capture bidirectional context and then outperform BERT based off of that. And so essentially at the time, it was doing really state-of-the-art performance on lots of things like text classification, question and answer. All of these things are changing so fast that it's hard to even make a YouTube video about it because in 6 months, they're sort of like already beaten by something else. But it gives you kind of an idea of some of the big things that have happened anyways. What I think is slick is that, all of these are relying on the transformer architecture, but not exactly how it was put out. In fact, nowadays, modern, LLMs and GPTs are only using the decoder portion of the transformer. If you remember back from our video on transformers, go back and check it out if you want. We talked about encoder and decoder, but modern ones are only using the decoder, where the process looks something like this. To train it, you tokenize the input because it can't look at an infinitely large amount of text. You have to have some region, right? You then pass those embeddings to the model. It produces an output. You calculate the error, and then you use backpropagation to adjust the weights so that it does better and better at minimizing that error. Okay. What was really slick, and I think what changed most people's minds about language models, if you saw Talk to Transformers way back in 2019, you might not have been very impressed. But when you saw ChatGPT the first time, it probably changed your mind and you were probably impressed. And that's because they achieved what's called alignment via reinforcement learning from human feedback. RLHF, reinforcement learning from human feedback. This has become a huge, very big deal because this allows you to take your language model that was just trained off of some corpus of data, and now you can encourage it, you can train it, you can teach it to give responses that satisfy some sort of alignment. Like maybe you don't want it to use racial slurs, or maybe you want it to not be so confident and to express some hesitancy if there's some uncertainty, right? All those things that we're training our language models to do comes from alignment. And here's how it's done using human feedback. First off, so a prompt is sampled from your prompt data set. A labeler demonstrates the desired output. So this is the human labeling part, right? You have to have some sort of labeling. So explain the moon landing to a 6-year-old. Okay, some people went to the moon, blah, blah, they describe how that works. This data is then used to do what's called fine-tuning of a GPT-3 or some other transformer, some sort of language model, right? With supervised learning, where you are providing examples of what the response should be from some input, okay? Then it says a prompt and several model outputs are sampled. So then, because there's this stochastic nature of generating things, you just let it generate several versions, right? So it explains 4 different things. And then some human, again, looks at the outputs and says, this is the best one, that's the worst one. They rank them, right? Maybe these 2 are similar. These are definitely better than those, though. And then that data is used to train a reward model. So this is a separate machine learning model that now is predicting the likelihood that a response would be scored highly or scored poorly, okay? And then that new prompt is then sampled from a data set. The policy generates an output. A reward model calculates the reward of that output, and the reward is used to update the policy going forward. This is reinforcement learning from human feedback, and it has been a big deal. It has made models really perform well. That said, there are some issues with ChatGPT. Remember in the early days when it first came out, people would Google the next year after it came out, they'd say, who won the Super Bowl? And it would just make something up. Because remember, it used to tell you all the time, like I was trained on data from 2021, whatever the day was, and earlier, I've never seen anything after that. And so that's a problem, right? To prevent it from doing hallucinations, but without having to retrain the model at enormous cost, by the way, certainly in the millions, probably tens, maybe even hundreds of millions to train some of these things. You're not going to retrain it every month when new data comes in, certainly not very often. So a way around that is to train the model once, but then to rely on something like Retrieval-Augmented Generation, or RAG, as a solution. This can fix lots of things. It can fix the problem with token size limitations and the need to constantly retrain data after a cutoff date. Here's how it works. You have a user query. So let's say I'm asking who won the Super Bowl, right? Now, the language model, when I ask the question, who won the Super Bowl, all that context, it knows what it's looking for. It just doesn't have the right data to answer to it. So what the RAG system does is it takes that query and it passes it through some sort of embedding. So now that's a vector. And then it has some knowledge base. So this could be the internet, right? And you could take that internet and you could periodically embed the internet, right? Do a word embedding. So you chunk the internet up. Maybe it's like per website, you take chunks at a time and you break it up into pieces. Maybe you don't have to do it on the whole internet. Maybe just do it on some smaller database. Like maybe you have an almanac of like sports games, and winners. So you go through that almanac, you chunk it, and you embed those. So now what that's going to do is allow you to ask when a user provides a query and that has an embedding, meaning you've taken literally a question and you turn it into like a mathematical vector pointing some direction in hyperspace. And you have all these different blocks of text which are available as well. And those all have been assigned vectors because you've embedded them. Well, that allows you to pick the vectors that are most similar. Here's your question, and here's like the 5 most similar vectors in terms of having the same content. So then you pass your query and that block of text, or several of those blocks of text, to the large language model. You say, the user wants to know the answer to this question. Here's the question. Here's some relevant blocks of text that may contain the information. and you pass it those. And then the output is really good. And Perplexity AI was one of the early great examples of this. You could ask it, help me find research papers using machine learning for material science. And it would find you real papers. Back at the time when ChatGPT was just making answers up, it would provide papers that looked like they were real, but they were not real papers. Perplexity AI, because it was using RAG, was actually pointing to real documents because it had put them in a knowledge base and used RAG to identify your query and the documents available, which ones are most closely aligned, to give you an output, which is really good. So really, really powerful technique. We've got some cool research going on in this area in my group right now. Another really cool area that's extending out of large language models is this idea of agents. So agents offer the ability to train large language models with different alignments and then have them work together in a system, right? So remember, what makes an agent, right? It's got instructions. It might have a specific set of tools. Maybe it's got a specific set of memory or things it's seen before. It's got whatever its large language model core that it's using. It's got some prerogatives about knowledge or planning, and you can make these work together. So for example, you could have a multi-agent framework like MetaGPT. Is actually, look at all the stars on that, 37,000 stars on GitHub. It's probably grown since then. Where the idea is, what if you made a system of large language model agents work together in the same way that a office works together, right? If you think of the office, you had the boss, you had the Dwight, you had the Jim, like the salesman, maybe you had like the HR person. You could train large language models with different functions, with instructions, with different prerogatives, such that overall, as a system, they work better together. This is really early days for this, but it is definitely something to watch. Very exciting. You could train one language model to be a skeptic. You could train another to be an optimistic explorer when it comes to trying new things, right? You could train one to be a rule follower and give it very strict rules to follow, and then have all these work together so that overall you don't just get one personality, you get more like human personality where there's lots of different competing ideas and concepts, and you can embody those in this agent process. Very cool. Okay, so there's so much more we could say about language models, but let's pivot and talk about how large language models are being used in material science. And I'm going to give you 5 examples, right? For data extraction, property prediction, generative models, automation and interfacing, and education. And these come from this really great paper that came out last year in Digital Discovery by Jablonka and many, many others. This was a hackathon that was held on large language models where they were asking, how can large language models transform material science? And then this was early days. A lot of these were still very much under development still, but they just showed all the crazy stuff that they were working on in this. And there's some really cool things. I'm going to walk through a few of them. Let's start with data extraction. We've been trying to mine the literature for materials data for a very long time, and it is super hard. Like here's 4 different papers that all came around in about 2010, 2011, 2012. And these are things like Chemical Tagger or Oscar or Chem Data Extractor, things that once upon a time were state of the art, but really were not that good. If you fed it a paper like a PDF, its job was to try and pull out things like the metadata related to synthesis or properties, things of that nature. And they were the best that we could do at the time, but they were pretty unimpressive. Mostly because they relied on semantic text mining, right? Which is sort of things like named entity recognition. So what if somebody uses a slightly different name for the same entity? It would, break it. Things got a little bit better because they realized that humans describe things in more complicated, complex descriptions than we thought. And if all you were doing was, say, looking at patent literature, then some of these tools actually worked pretty well on patent literature because there's a very specific way that you're supposed to talk about things there. But in general communications, it's much more complex. And so scientists moved away from semantic approaches to natural language processing approaches. And this paper on the right, this one in Chem Matter, came out in 2017, just before Transformers. And I remember seeing it at a conference, and these people I respect, I think they're awesome. But I remember thinking like, God, this is a good idea, but I just don't think that this is ever really going to work. And boy, was I wrong, because shortly thereafter, we saw transformers show up. BERT, for example. BERT gave rise to SciBERT, which gave rise to ChemBERT, which gave rise to MatSciBERT. And now what you saw was large language models training off of increasingly specific blocks of text, like just material science data or just chemistry data or whatever. And so you had these pre-trained models that learned relationships really effectively in specific domains. And this led to a big jump forward in the progress of extracting data from literature. But the one that really changed my mind was this paper. The preprint showed up here in December of 2022. The full paper came out I think it was just this year in 2024. And this was by the folks at Lawrence Berkeley National Lab, UC Berkeley, Sater and Jane and others groups. And really what they did is they used ChatGPT. They used reinforcement learning from human feedback to build these now better language models, essentially. And this allowed them to do things like take training data where you had a paragraph of text, turn that into some JSON structured data via manual annotation. That sucks. They had to make 100 examples of that, which is a pain. But then once they had that, now they could create a partially tuned language model where it would now do its best to generate an outcome. And all they had to do was look at that and then babysit it and fix the 500 examples and then retrain again on that. And now you have a fine-tuned large language model, which could really start to do the types of things that we're interested in. And we've seen this type of approach now in many places. Like here's some applied to perovskite solar cell literature, right? Where they were able to use the same approach, a fine-tuned LLM. So you take a language model, now you're going to fine-tune it on some, example, subset of data. And it does a really good job of extracting data. Here's another one. So showing dramatic improvement. And again, it's based off of this idea that you are training it with telling it how you expect it to respond, right? So step 1 is collect and demonstrate data, train a policy, we've seen that. Step 2 is going to be collect comparison data and train a reward model. And then 3 again is use that policy to reinforce and learn. So just like we saw with ChatGPT. And then ChatGPT chemistry assistant for MOF synthesis, same thing is applied here. Here they're using it at several different steps. Here's another one where they're using materials data extraction for using general purpose language models. And they sort of explore different ways. They try zero shot, they try human assisted, which is fine tuning, and then human assisted data structurization. So there's various degrees of human involvement and human labeling in these different approaches, but we're seeing more and more papers show up all the time, which is pretty exciting. So in January 2023, that first paper came out in December 2022. That next month, me and my group said, well, let's give this a shot. And we were blown away. You can take a paragraph like that, and with a little bit of fine tuning, you can get a model to spit out really nice structured data like this, right? That thing, which is really like a human has to go through that and read it and understand it, can be broken down into, for example, synthesis metadata really effectively. But there were some areas for improvement. For one thing, the original paper was only looking at the abstracts because of token size limitations. It was just too difficult to, we didn't have a model that could look at a full paper, which might be 20 or 30 pages and, tens of thousands of tokens. And so instead they would only look at the abstract, and some information's in the abstract, but certainly not everything. There's some other problems. The other one is the hand labeling. Even generating 100 examples is a pain in the butt. And then babysitting another 500 is pretty miserable. So what if you could use some other source of labeled data, like for example, data in the polling file, which is just, humans they've paid retired engineers, I think that's how they do it. They basically pay subject domain matter experts to read papers and extract data from them. So what if we took those, we linked it to the paper that they extracted it from, we turn that into a representation of the data with reduced tokens, and then we train a model off of those. That could fix both our problems, both the token size problem and the hand labeling problem. Okay, so there's lots of tools for doing this. Meta's Nougat, for example, is awesome. It allows you to convert a PDF into markup language, which is great. It also does a really good job of even converting tables into markdown language. Really, really effective at this. So we did a preliminary study where we set up to try and understand what types of data live where in materials journals. So this is from Hassan, Wade, Sterling, and myself. You can find this published in Matter, but it's pretty slick. We looked in literature and we asked what data is out there. So if you look in the text, what do you find? You find things like named entities. Those are the things circled in purple, like formula names. You find processing conditions, like, okay, this was annealed in a vacuum sealed tube furnace for 168 hours at 673 Kelvin, right? You find characterization. Standard X-ray diffraction was used with copper K alpha radiation and transmission electron microscopy, right? You find performance, like the spin polarization values were this and were that. Those are the 4 types of data that you're going to find. And then where do you actually find them? Well, you can find them in the text. You can also find them in tables. Here you see an example. The first 2 columns represent named entities. The next column would be processing conditions or characterization, in this case characterization. And the last one is going to be your performance or your properties. Here's another one. In figures, you very often see This is processing conditions and characterization, perhaps held here. This one is mostly going to be performance properties all stored into it, but it also has a couple named entity recognitions. This one also has named entities in it. So we looked at a bunch of different papers and we asked, what types of data do you find in what different formats? We looked at text, and on all those papers, we found that about 50% of the information there is named entity. We have a small fraction of processing, a little bit more of characterization, a little bit more properties. But look how different that is in tables, where now characterization is a dominant thing that gets reported. And then in figures, it's dominated by performance properties. So very different types of data get stored in text versus table versus figure. And if all you're doing is extracting information from, say, text, you're probably missing out on a lot of the performance, was one of the key takeaways here. Okay, so yeah, the takeaway from this is like, boy, it all of a sudden seems possible to go from PDF to text mining, but probably not all the data that you care about is going to be present in the text or tables. We need to figure out how to extract data from figures because we're not very good at it yet. Okay, then the other question was like, okay, what about token size reduction? There's different ways of doing it. You could do rules-based extraction, like you could feed it a whole paper, and then using rules, you could have it pull out just keywords. Like you could say, look for anywhere where there's a number and then return the words near that, right? Give me like the 5 words prior and the 5 words after anytime you see a number, or a certain unit, or a name of a furnace, or whatever else, right? That would be rules-based, right? You could do extractive summarization, where you provide hand-labeled examples of, okay, given this big block of text, this is the part that I really care about. Summarize it in a really concise way. There's zero-shot summarization, where you don't give it any examples. You just say, do it. You give it the instructions and say, do it. Or you could do one or multi-shot summarization where you provide examples. Sometimes that gets called structured prompts, right? So here's an example of zero-shot summarization. All we say is summarize the text. And it goes from 157 tokens down to 58. And it loses a little bit of information that you probably wouldn't have wanted to lose, like some values got left. So here's another one. This is zero-shot summarization, but this time with better instructions. So we say, make sure to concentrate on and provide any pertinent performance metrics, measurement results, or related numerical data while keeping the information concise. So again, it went from 157 tokens down to 50, but it did a better job of preserving some of the information we care about. But that's still a zero-shot summarization. And it didn't always work, by the way, because this is sort of a stochastic process. Sometimes it works great, and sometimes it returns totally nonsense and it hallucinates. Bummer, okay? That said, it does do a pretty good job of identifying some key categories. It knows that these things are all like reagents, and these things are preparation approaches, and these ones are analysis methods. It does a pretty good job of identifying those, even though it does occasionally do some really big mistakes and just mess up. So the takeaway 2 from this is we probably need fine-tuned models for material science data extraction. Generalized LLMs are probably not going to be good enough for this. And to fine-tune them, we're going to need gold standard annotated data sets, which we don't have and are a pain to make. Okay. So the polling file in the MPDS does provide some cherry-picked data. It's not as good as we hoped. I was hoping we'd have like all the data in a paper, but when we actually dove into it, we realized they only took like certain values. Like if data was represented at 300, 400, 500, 10, 1,000 Kelvin, maybe they only reported a few of those, which is a bummer. So it was cherry-picked a little bit. So next we asked whether we could do structured prompts using Gemini Pro. Yeah, the same Gemini Pro, which was in the press for all the wrong reasons. We wondered, no need to throw out the baby with the bathwater if it could do some good things. And one of the cool things that Gemini Pro does is it offered structured prompt as a simple workflow. So the way that structured prompts work is you're still going to provide a prompt like, listen up, you're a lean, mean materials data extracting machine. You're going to focus on this and that and that and that. But then it allows you to give examples like, had this been the input, right, some sort of text from literature, this is what I would have expected. This is some sort of structured JSON output, right? And you can do this really, really effectively with only a few examples, not 500 like you saw with the fine tuning. You can do this with maybe 10 examples, really a reduced set. You can use this structured prompt approach to have it extract data really effectively. So here's an example. Here we used it. Here was an original text, and here was an extractive summary, right? Huge ability to do token size reduction. Here's another one. A big block of text, turn it into a structured data set where it's in JSON format. We can actually do machine learning with it, right? So we tested this out using Google's Gemini Pro, and here's what we did. We tested the performance on 10 papers, the entire text, not just the abstract. We chunked the paper into chunks, and we did pass the whole thing through. We ran structured prompts for only 5 examples. I think it was only 5, that might have been higher, but it was very few examples. And we went section by section through, and we repeated the extraction 5 different times. So I had 5 different group members all try it so we could see the variation in the output. And then we compared the generated outputs with something hand labeled in order to create a reference score for performance. So what scores do we use? You can use Rouge score. Rouge score basically says, like, if the model said, the hello, a cat, dog, fox jumps, but it was supposed to include the words, the fox jumps, then the Rouge score would say, oh, why, it has all 3 of those words. It has the, it has fox, and it has jumps. But it also had 4 words that were not supposed to be included. So the precision is actually 3 out of the 7 words. 3 of them were correct, 4 were not. So it's 3 out of 7. That's how it calculates precision. And you can also do recall. You could say, like, okay, the recall was actually perfect. And so even though it had perfect recall, it had less than perfect precision. So you could calculate something like an F1 score if you wanted. That's Rouge score. What's the downside of this? Well, a couple things. First off, word order is not included anywhere. That's a bummer. And what if it didn't use the word fox, but it used wolf? Well, fox and wolf are kind of similar. Should you get some credit for using the word wolf instead of the word fox? Maybe you should. In other words, there should be some contextual understanding, and that's where transformers come in. Things like the BERT score is a really good tool for this, because BERT score takes an entire phrase and it turns it into a vector using contextual information obtained from, voila, transformers, right? So for example, the reference says, the weather is cold today. Now consider, what about the candidate phrase, it's freezing today? Well, it's not using the word weather, but it's talking about freezing and cold, right? And so it's more correct than the Rouge score would give you credit for. So the BERT score is I think a better way to do this. It takes into account word order and sort of synonyms or close misses, and it's an effective tool. Anyways, what we found is that when we did this structured prompt using Gemini Pro, you get pretty good performance. The Rouge scores are just okay, but the BERT score was really great, okay? So our takeaway is that structured prompts, we think, could really greatly reduce the need for manual annotations, which would be pretty awesome. So you can follow along with our developments. We just got this paper published in IMMI, one of my favorite journals. So you can check it out. Here's the link to it. But there's so many other things that LLMs are doing. You can use them to find patterns in words, but those words could be properties. Now, these are some crazy papers. These are on arXiv. They're not peer-reviewed yet. And some of their claims are just completely nuts. Like that top paper says, predicting physical and electronic properties of crystalline solids from their text descriptions, where in the paper they go on to argue that their large language model is actually outperforming graph neural networks, like by significant margins, which is, you got to swallow hard to believe that, but maybe. I haven't seen what's become of this, if it's actually gotten published or not. I haven't looked into it. But the fact that they're even making that claim is exciting, that maybe, there's new ways to use language models in ways we've never thought of before. Take a look at this bottom one. Again, here they're saying that GPT molecular features from a language model are basically outperforming smiles. It is a better representation than even smiles. Pretty broad claims happening. There are some really cool papers that have come out for going from materials to predicting properties using language models. The best one is this one. This was by Jablonka and Smith and coworkers, where they show that in comes a smile string, and you can actually go ahead and predict things like what's the boiling point, or all sorts of different things. And they show that it's actually surprisingly effective. Very, very cool paper. There's another cool paper by Luisa Antunes, who's a friend of mine, actually with Keith Butler and Raghav Crespo. All these guys are friends. Amazing paper here where they use a large language model to predict essentially sieve information. And once you've got a sieve information, you've got a new structure. So just like you can have a ChatGPT tell you a story with new words, that's a new story, they use that same idea to generate new structures. Now, there's a lot of problems with this, I think, but it's an amazing idea. Super cool approach. So that's just a sampling, a smattering of some of the things that we're seeing with large language models right now. There's a gazillion more things coming down the line, but I think this is enough to sort of pique our interest that large language models are probably here to stay, and they're certainly enabling exciting new things in materials. So stay tuned for more updates on this topic.